So hello everyone and welcome to my talk, Make the Bytes Speak to You. Today we're going to do a short introduction into the development of dissectors and what to consider when you write the dissector. This is a beginner level course, so we dive into coding a little bit, but it's more focused on the general pitfalls you're going to have when writing dissectors, what to consider, what to think about. A little bit about myself. I have been a Wireshark core since 2013, or Wireshark contributor more likely, Wireshark core since 2016, software developer. I've been now for about 23 years it is. Based in Austria. My day-to-day focus is more on team management and software development in the intercom area. What we're going to talk about is we talk a little bit about the cookbook you should use when you write dissectors, the ideas, the topics behind writing dissectors, features to be used. We're going to take a look at the generic how to write a dissector in general, and as well as how to get informative dissectors, how to get dissectors that are actually really can be used in a productive environment. And we're going to talk about what code should be looking like, how to submit code in general. Well, let's start with this question. This is actually a question you should ask yourself whenever you write a dissector or whenever you update the dissector. It's not so much what I want to do, but it's what more to the point of what is my audience. When you take a look at Wireshark dissectors, you often see that there's a great variety between different dissectors and dissector styles. More often than not, dissectors have been written in a very technical point of view and in a very technical way, and we're going to talk about it in a second why this is actually a good thing. But often you come across also dissectors, and I give an example later on of in my opinion, of a not so good implemented dissector that hasn't been written with the audience in mind, but with a different audience, which actually makes it really hard to use the dissector and makes it a really bad thing to be using. So ask yourself those three basic questions: who, what, and how. So who is going to look at the packets with your dissector? Who is actually doing the dissecting after you're done writing it? We all have come up with writing some code at one point, or at least scripts. In my case, I started writing Wireshark code by actually writing a dissector for a machine safety protocol. And in my case, it was to learn that protocol, which is a really good way of getting into writing a dissector. But on the other hand, I had no experience of who is going to do the dissection, which in this case actually worked out pretty well, because now I wrote the code from a point of view with very few technical knowledge about the protocol, which made the dissector great to use later on, because most people who use the dissector actually have very little knowledge of the protocol. So that's the second question. What is the level of expertise of the person doing the dissection? Is it a day-to-day technical guy who has deep backend knowledge of the protocol you're using? Like, for instance, do you have a dissector that like TCP, that is used a lot by guys who are doing a lot of internal TCP dissecting, or you have a very esoteric protocol which is only used by a few people who actually wrote the protocol most of the time itself and use the dissector for debugging purposes? And the third thing is, how is the dissector going to be used? So it's very different to write a dissector that's mostly being used by T-Shark. So this is actually a thing when you have a protocol that is most common used in data centers where you have high bandwidth connections, or if you have protocols that are going to be used in the cloud. Then maybe the people doing the dissecting and doing the technical support and the technical expertise come from a very different background and experience. And so when you have certain mechanics in the dissector, certain ways of naming stuff, which is basically what it comes down to, then they might not be used to it. Or in case of T-Shark, if you have a very long filter line and you have to pre-filter whatever you're seeing using display filters, then you're going to have a hard time, because you end up pretty much with very large command lines. And in a real world, run into delimiter limits where you are not allowed to enter all the dissector levels you're going to need because, for instance, there's a limit on the size of a single command in the bash or in Windows command line. So this is also something that you have to consider before you start writing your own dissector and to get behind it. The second thing is actually something very trivial. So, but at the same time, it's very complicated to use. So for instance, in this course, we're gonna write a dissector for a tool that's called XCAP example, which is a Python script which creates kind of a predefined protocol and is used as a debugging tool for the XCAP interface Wireshark provides. And the first question I'm gonna come up with is, what is my protocol actually, what is it actually named? So in my case, we don't have any protocol behind it. It's just some Python interaction I hacked it together a long time ago. And so I have no clue what I should name it. So in this case, I just name it example. Oh, by the way, all of the stuff you see, all of the code you see, you won't be able to download it from any site because it's going to be mainline. So I'm gonna be putting it in the main Git repository for use later on as a reference together with the XCAP example. So the first thing is, what is my protocol's name? If you're building on an existing dissector, this has actually already been decided for you. But if you're creating a new one, then this is actually a really difficult thing. And consider in this case display filters. So for instance, I have now two varieties of display filters. The first one is a very easy and useful one. It's called example message length, which basically tells you that you have a protocol. In this case, we name it example. And for whatever reason, this protocol has a message, and this message has a length. Now consider the second one, which sounds as easy as the first one, example protocol message length. But the problem here is that you're gonna face a lot of guys who come from Unix background, and Unix guys are not used to writing camel case variables, for instance, or could be thrown off by that. Especially if your protocol is running on top of another protocol which actually doesn't use camel case but only lowercase. For instance, when you come through OPC UA, you're going to see a lot of protocol names where suddenly you're running on a TCP stream or you're running on an IP stream, and suddenly you're seeing camel case namings and camel case display filters together with lowercase display filters. And this makes it actually really easy, really hard to remember what you want to do, and really hard for people to memorize those filters, so they have to look it up all the time, and it makes it harder to dissect your protocol than it actually needs to be. So this is something to consider. My recommendation at this point would be to stick with the lowercase because it's actually easier for you and it actually makes more sense. Because with lowercase, you are kind of limited to the expression, because if you write example protocol as your lowercase, it will come really scribbled out. So you have to think a little bit more about how to write it. And the second thing is, most of the protocols in Wireshark are actually lowercase in the display filters or general naming. If you need something like example protocol, use an underline. So example underline protocol would be a valid consideration in this case. One side question here is two things, actually. The first one is legal considerations. Now, most of us work for companies where the protocols are actually either being developed or actively being used. So the question here comes up, am I legally allowed to present this protocol in an open source environment? This is where a lot of Asian ASN1 stuff comes into play, because most of that stuff, especially during development, is still under strict legal guidelines. So you're not allowed to create an open source dissector for it, but you might be at a later point in time. And there are tools which I'm going to show you in the source code in a second, where you can actually write the dissector already, but make it open source when, for instance, the specification goes live or goes open source. The second thing to consider here is trace availability. So when you create a dissector, chances are that it's a little bit more extent than the example protocol I'm going to show you in a minute. And the problem with that is that the example protocol, actually, it has about 5 fields, and it's very easy to look up. We don't have any documentation for it because it's just the Python code itself. But in a real life scenario, you're going to have a lot of fields. There are dissectors out there that have really literally thousands of fields available. again, the OPC dissector comes to mind. So think about when you put this in an open source application, we're gonna run our own tools. We're gonna run certain tools like FastTest and similar stuff that creates captures from pre-existing captures, and we manipulate them in a certain way to consider the edge points and the fringe points of your dissector code. So in that case, we can find issues where, for instance, a certain end limit hasn't been guarded correctly, or you didn't consider the end of a message correctly and stuff like that, and we can actually create bug entries for that. This makes it much more stable, much more easier to debug the code if this is available. But if you create a dissector for certain private or close guarded code, which has certain special interest stuff in it, which is only available really in high-end hardware or just in the hardware that actually is only available for your own company, then it makes it that much more difficult. A solution to that could be Scapy. Scapy is a Python tool which allows you to create basically a packet on the fly, so you can use Python to manipulate it. And this would allow you to create traces which are free of considerations that are, from a legal point, problematic, and actually could really test certain possibilities in your protocol. Scapy can be used in a second way. So if you have a protocol where you have certain edge scenarios which are not often occurred that much in real life, you can use it to create certain traces that only show this problem, and you can create then the dissector code for it. So usually I would say it's a little bit the same like in modern software development predicament, where you say write the test first and then write the code for it. So in this case, I would say if you create certain stuff for dissectors, see that you have a trace for that stuff first, or that you write a trace for it first with Scapy, for instance, and then write the dissector code. It makes your life that much easier, and you can guarantee that it really does what it should do. And second thing to consider, the dissector I wrote back then had about 250-page specification in it. I think at the end of the day, I found pretty much every bug we had inside the specification where the specification didn't behave to the real life scenarios or real life implementation, or vice versa. And the reason for that is that when you write code and you use Scapy, for instance, to create traces that mimic what is in the specification, you pretty much run across all those implementation errors. So it's actually a really good debugging tool for your protocol implementations as well. Now, before we dive deeper, let me just talk a little bit about how Wireshark works. We're going to create a dev, or show you what you can do to create a dev environment in a second. We actually saw this image about an hour ago, which I was kind of surprised. This is the web page where you're going to find it. And I just want to go to put on two things here. First of all, we are all used to firing up Wireshark and capturing. The problem with that is that actually we do a lot of stuff before you can do that. So for common systems, you have your WinCap situation here, you have a libpcap situation, or with new installations, mpcap on Windows, where you have your capture engine. With Wireshark on top, you have another capture engine, which is called dumpcap. So actually, Wireshark itself doesn't capture anymore. That was done in older versions of Wireshark, but in newer versions, we use this dumpcap utility, which does all the capture stuff. This includes also XCAP. The reason for this is that if anything goes wrong with the capturing, Wireshark still lives on. And more importantly, if anything goes wrong with Wireshark, dumpcap can still live on. So if you're in a long-term capture and Tshark crashes, which you used to record the capture, chances are the dumpcap is still running. And if you do that, writings captures data to files, then you will still end up with the files. There is one exception to this rule, and that's Wiretap. Now, Wiretap is our file loading engine. So whenever you load a file, you pretty much run up a Wiretap dissector, which is also a dissector, by the way. And it is used to loading the file. Everything runs into the core, and here is one thing you have to consider. The main packet we have, the first dissector that's being called in our system, is called frame. So whenever you see some Wireshark packet detail and the first sector is called frame, that's the first entry is called frame, that's really because that's the first entry called. There are a few exceptions to the rule, but in 99% of the time, that's the first one. And everything else that comes beyond frame has to be explicitly called. So it's not that Wireshark by magic figures out which protocol it needs to dissect, but you in your protocol have to decide how the dissection engine is being called. Now, one little sidetrack I want to show you here is I actually have here the Wireshark source code open. So I'm just closing this down a little bit. One small step I want to show you here is the tools directory, because this is often overlooked when you open up Wireshark. You see you have a lot of stuff in there, but what you also have is quite a few files called something-setup.shell. Now, those files actually are really neat when you do a new development, because those files do something. For instance, here's the macOS file. They create your development environment for you. So if you want to start developing with Wireshark and you have no clue what you need, what you're gonna need, then you can run those setup tools. You end up, I would say, with about 99% of all the necessary libraries. There are a few exceptions to this rule, but most of the standard libraries are in there. You might miss some speak codecs. So for if you're doing some telephony stuff, you might miss some codecs in this version. But most of the stuff gets installed. There even, sorry, he jumped back into the dissector directory, which we come in a second. There even is nowadays, no, Windows is not here yet. That's the reason, because Windows has a very extensive stuff, but you have a PowerShell script you can use to set up your Windows environment as well. Now, this stuff is being kept up to date. So usually if you just check it out, you should end up with a pretty recent development environment, and we're making sure that this environment works. You can obviously do the installation of the environment yourself, and there is a lot of stuff yourself that you can benefit from. But in most cases, it makes sense to use those setup scripts. Now, let's talk about fields. One thing that most people don't know is that we actually have a display filter reference. Now, for display filter reference, I'm just going to this, this URL real quick. One sec. So this is a list of all the protocols we actually have in Wireshark, and with all the fields they have in Wireshark, which is an automatically generated site. So currently it's run on 3.2.7, so it's not taken in consideration development versions. But let's jump, for instance, to TCP. So you see here you find the transmission protocol. You see in which version the transmission protocol has entered, how many fields it has. And you can click on it, and then you see every field this protocol actually implies with the description the field has in Wireshark itself. This is coming directly from the source code, and the type of the field, and in which version it was introduced, and in which version, in some cases, it stopped working because it was removed. Now, when we take a look at those fields, you see that most of them follow a certain semantic. So you have, for instance, you have, this is your TCP is your main name. So your main protocol name is called TCP in this case. Then you, for instance, we are here in the connection area. So you have a connection subset, and then you have certain flags for the connection levels. And also you see that they pretty much all follow the same consideration. So in this case, you see that all of them are lowercase. All of them, if they have two words, have this underscore in them, which makes them very easy to remember. So everybody of us knows IP port, for instance. The reason why you remember IP port is because it's very easy and very recognizable. It would be very hard if it would be called Internet Protocol port. But there's also, wherever there is light, there's also darkness. And my personal favorite, I'm not dumping on the guys who did it, But my personal favorite is the OPC-UA dissector. The OPC-UA actually is a dissector that comes more and more into play because it's actually a really important protocol in certain industries nowadays. And the problem with that is that it had been developed by a bunch of different people with different knowledge levels and different ideas behind them. So you get stuff where you have OPC-UA, okay, they all agree that OPC-UA should be written lowercase, which actually doesn't need to be, you could change it up if you want to. But they all agree that it's OPC-UA. And then suddenly you have camel case, then you don't have camel case. This is actually something that's really interesting to me is OPC-UA array length, OPC-UA array dimensions, OPC-UA array size. You would assume that everything that's an array and has to do something in the end kind of is written the same way. So people always have to think if they need an array length field and they have to write a filter for it, they always have to think, is it lowercase or uppercase or is it something in between? The second thing is that this doesn't really tell me anything. OPC-UA array length doesn't tell me where this array is residing in the protocol. It doesn't tell me what actually is being used. And it really is a bad example here in this case, because OPC-UA array length is actually not a field at all. It's an expert information. So it's something that you put into the dissector if something went wrong. OPC-UA array size is used in 10 different variations all through the dissector on different fields, which are very less connected with each other. So you actually don't really can look it up. You can't use those fields because you can't use those display filters. And this is actually, and I'm speaking from experience here, this is actually one of the huge problems we have when we want to dissect OPC-UA, because you can't write display filters for it because they just don't work. You have no possibility to get to the right levels where you want to query something. And this is a huge thing you have to consider. It's often overlooked because you just come from memory, you just want to write some stuff. And this is actually one of the biggest caveats most end users have if they leave the fringes of the normal protocols like TCP, IP, and consorts, and go into factory-specific or industry-specific protocols. And most of the time they run across stuff like this. And then they're gonna have problems because they can't write display filters. They can't memorize stuff. They have actually, I've seen people who have books, actual books, handwritten, lying beside the desk, would have written down all the necessary required fields. And in some cases, it's, if I want to do a section or an error analysis on that, I have to use this display filter, then go into this packet detail and then look up this value. If this is the case, then do that. They can't put it in the column, they can't put it in some text, so they have to do it manually, and this literally is thousands of protocol. Yeah, Graham, I know, but that is one of the big problems. And it's actually not excuse because somebody wrote the generator, right? So somebody had to be able to write the better generator for better or worse. I'm just dumping on OPC-UA because it cost me a lot of time in the past, but yeah, there are other examples out there. So let's come back to implementing now the dissector. Now we have decided on what to name our dissector. I'm gonna name a dissector example protocol dissector. I'm gonna shorten it to example because that's pretty much what it is. And I'm using the lowercase example for that. Now, my first question is, where am I located? Now I'm gonna fire up Wireshark real quick. And this is Wireshark running here in my nice little system. It's the 327 Wireshark, and I'm just running this example stuff here. Now, I don't have any dissector written yet. So it's, this is just code, and I'm stopping this that's being generated. And as you can see at the moment, all it does is it generates an Ethernet frame with an IPv4 packet in it, which really is just generated on the fly, so it's not transmitted over any stuff at all. And then it has some data written into it, right? Which is easily readable in the byte view. We could employ Gerald's new, let's see if this works on the fly or if it crashes. I've actually never tried that. No, it's we are in 327, we can't use the packet detail yet. So where would we hook it? Where would we start to write? Now, this protocol is actually residing underneath IPv4, and in IPv4 it uses a protocol field, and in this case the value 254. So I'm mentally writing down 254 and the IP protocol stuff. I can also take a look here in the bottom, ip.proto, which we'll come back in a second. IP is actually a really good protocol in regard to writing the sectors for. If I don't have this luxury, if I don't have the availability that I know, okay, I'm always being in this sequence, I'm always running underneath IPv4, and I'm always running it underneath as a protocol number 254, then I have to think of other ways to do it. So the easiest way to do it would be to just write for IP.port or TCP.port or UDP.port, for instance. A lot of the sectors are written that way and connect there or other stuff. But there is also a second class of the sectors I'm coming up in a second. Now, if I know, okay, it's IP.proto, I can look it up, for instance, again in the source code. So I'm going back to my source code here. And I'm searching in this vast example. So I'm back in the Wireshark source code. I'm underneath the EPAN directory, and there is a subdirectory called the sectors. So in this sectors, you're gonna see a lot of packet miner stuff, which is actually every sector we employ. And there is at some point is this packet IP.c sector, which is a huge file. And you don't have to look through it, but there is there's actually a function which I mentioned now here, which is called register the sector table, and I'm gonna just look it up. So I'm going register this sector table. Now I see, okay, the IP sector in this case has two of them. So I have an IP proto hook and I have an IP option hook, which actually means that I can write a sector for the IP protocol, either for implementing a real protocol, or I can even write a sector for an IP option, which actually works. There's a third thing here, which is a heuristic dissector list. Now, a heuristic dissector is something fun. A heuristic dissector just assumes that you run under a certain protocol. It doesn't assume anything else. So in this case, it says, okay, whenever the IP dissector is running and it comes across a certain data values, basically the end of the data it can't dissect after the IP header, then it goes through the list of the heuristic dissector, and every dissector that has connected to that list is asked, do you want that packet? And what your dissector then has to do is actually, sorry, I have to switch back here. Is actually then register itself to this list, and with this registration you're gonna get this hook, and then you get the data bytes, and you can decide for yourself, is this a packet I'm applying to, or is this not a packet I'm applying to? There's extensive documentation for it, and I always give the recommendation to use existing dissectors to look it up. But it's actually quite a cool thing to do, and in some cases it's the only possibility to actually dissect something. But let's take this registration stuff to the real world, because it's actually kind of abstract to just read about it. So again, I have this IP proto, and I have decided in my Wireshark back here that I want to imply this IP proto because it's 254. This is actually what I'm gonna writing for. So I have already created a small source code, which I'm gonna be using. This is a packet example. It's residing under my EPAN dissectors. And the second thing I have to do, going back up this whole list, is I'm gonna have to tell the Wireshark source code that it has to compile this stuff. Now there are two possibilities. One is I can change CMake list txt, which is the build file descriptor for all the files built with Wireshark, or I can use this CMake list custom txt. Now, the CMake list custom txt is there for a reason. If you're building a Wireshark version specific for your company, or an in-house Wireshark version where you want to add some protocols, but I don't want to change the base source code of Wireshark, you can add those CMake list txt files CMake list custom TXT files, and you can just add your stuff in there. Wireshark will look for them, pick it up, and then compile it as if it would be the same stuff from your own, from an internal source code. Makes it very easy to update the base source code of Wireshark without having to reiterate your dissectors in it every time. But in my case, we're gonna change CMake list TXT. So CMake list is a long file. But what we're looking for is actually, you see a lot of stuff up here. You see some packet, blah 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 stuff, and clean, whatever. We don't care. What we're caring for is there's a set dissector public headers, and if there's a set dissector public headers, there's also a set dissector source. This is actually what we want to look for. And I just went ahead and added here this example. As I said before, this source code will be part of the main Wireshark source code base, and I will put up a link to the merge request in Discord later on when I have done the commitment. So you will be able to just download it and play around with it the same way I'm doing right now. So with that in mind, let's close this one because I don't need it anymore. I'm going back to this packet example. Now, this packet example is just a template file now I created, which handles the absolute minimum of creating a dissector with a little bit extra already added to it. I'm just going through it a little bit. There's an extensive documentation on the Wireshark development wiki. I'm going to show it to you later, where you can read the specifics for it. But in general, it goes like this. So you have a header on top where you say, okay, this is my dissector. It starts with the file name. And then it tells you just what the dissector does. You can write your own name. I would actually, if this is a company-driven protocol, I would actually recommend just putting the company name in there and some contact information and a copyright for the protocol itself. Then this is mandatory. The Wireshark traffic analyzer copyright has to stay in there, and all our source code is licensed with GPL 2.0. You have to include the config H, which is a basic configuration stuff, and in most cases, it uses just include EPEN packet H to the example value, and we created tree value, and this example value. This is just copy paste. You can copy paste it. You don't really have to understand the baselines for it. For this stuff, we come back later. And then you have to do two definitions. One is proto register, name of your protocol, and one is proto reg handoff, name of your protocol. So what Wireshark does during compilation, it goes through all the packet files, actually goes through every file that's in this array in CMake list TXT for the dissector source. It loads the file, it looks for those two functions in each file and creates a special C file, which it later on loads when it loads itself. And those two files, the register one and the register handoff one, actually create all the data structure you have to know for your protocol. So instance, for my protocol, which is this Python XCAP example Python, I know that I'm gonna have 5 fields. So I'm gonna have a verification field. I'm gonna have a remote interface name length. I'm gonna have the remote interface name, message length, and message data. And as you can see, I already considered how to rename the display filters. So we have an example verify, which makes it very easy to use. We have a remote length, remote name, message length, message data. So every time somebody says, okay, I want to look up for the example interface, then you can go to example.remote.name, and it's very intuitive to use. Yeah, this is, you have to register your subtree, which I don't go into detail, but again, in the development documentation, is it in there? The expert info will come to at the end to it. Then you create a module for it, and this is actually the real neat stuff. So you have to register protocol, and this is where the name comes back in. So we have in Wireshark, we have a long name for your protocol. So in this case, I named it example dissector implementation. We have a short name for the protocol. I just named it example. And we have a display filter name baseline for the protocol. In my case, it's example with a lowercase. This is mandatory that you put all 3 in them. And I would recommend doing it in a similar fashion. So example, for instance, is used when you disable protocols, then it's just use the smaller name. Yeah, you have to register some stuff, which we talk about in a second. You can register some preferences, which we talk in a second. And then this is the next big thing. You have to register your dissector. So again, I have this proto example, which I created here with the proto register protocol. And I tell him what it's called again. And that dissect example, that this method exists, which will get all the information if this protocol is being called. And then I have this rec handoff. This rec handoff is now the magic that tells Wireshark when to call my protocol. And in my case, I have this handle here. It's telling him that there is a dissection registration called ip.proto. And whenever you see the value 254, please call my protocol. In my case, in this example, my protocol does nothing more than just say, okay, I'm the example protocol by mentioning in the protocol column. And this is actually code that I can build and run. So I can create Wireshark here. I can zoom in a little bit and you see, okay, we do have now this example protocol. We don't have anything here in the case of data anymore because we are telling Wireshark we have everything we need to dissect the protocol, although we haven't done anything yet. But we already written into the protocol column, okay, example protocol is being used. So I know, okay, the registration works. But this is only half the dough, right? So this really doesn't give me anything to work with. Now let's see what happens if we add some magic to it. Now in this example, I have still my little protocol information for the example in here, but I already added some fields to it. Now fields in Wireshark are called proto items. Proto item is everything that's part of a protocol. Proto item can represent a subtree. Proto item can represent an actual field itself. And it has to be some kind of registration for it as well. So in my case, I extended my dissect example stuff by adding a tree to it, which will then, this is what you see in the packet details, the tree that you can extend, and then you see the actual fields for it. And I added a field example remote length. Actually, I made a mistake here, but we come to that in a second. Now, this is the name of the field I added, HF example remote length. Now, wait a second, we saw that above, right? There it is. And the registration for it is in this, on the proto register example in this structure here. So I'm just telling, okay, we have an HF example remote length. It has the name remote interface name length. It has this display filter, and it's a 2-byte unsigned integer field with a decimal value. And if I run this example, I get an error. Oh yeah, it's C code. That's, I really like my C code. GUI and 8 length, sure. So again, we have our Wireshark here, and we run our dissector. So again, we have our example, but in this case, when I click here, now we see something. We see the actually long name of the example dissector implementation, which is taken from the register protocol stuff. We see on the right-hand side that it actually considers all the remaining bytes in this case. So all the remaining bytes of the packet. And if I open it up, we see that it has 2 interface name lengths fields in there. Well, it actually really does, because it's telling me the first 2 is an interface name length and the second one is an interface name length, which is true. So it says, okay, starting with the first byte, the first 2 bytes is this field, and starting with the third byte, 0, 1, 2, The next two fields are this field. So actually it's doing everything right? No, because we see here it's the value 03. Well, that's another thing to do when you write the sectors. Some people are just not considerate enough if they write the protocol. This is the actual code that generates those packets. And as you can see, the actual code, this is the line that generates the stuff that's getting streamed over the in this XCAP interface. And as you see, this is a string. So we are not transmitting 03, we are actually transmitting ASCII0, ASCII3. So we have to figure out a little bit of code to get to the values we actually need. But we also see here already the protocol format. So we have a 2-byte length, then we have the remote name, then we have a 2-byte message length, then we have the message, and then we have this verify. We have to be considerate because this verify apparently also it's a single character, it's nothing else. Yeah, so we can close this again. Here we go. So this code isn't working. Well, let's do it really complicated, and that's pretty much my way of thinking. But I'm thinking about doing some stuff generically more or less, and yeah, I used to end up with a lot of complicated code normally. So please bear with me if you think this can be written easier. So again, I have I set my column, I set my info clear, then I have my tree build up, and now I read the length, the first length. So this is actually the remote length. Before I go into detail how I do that, let's consider first the offset. What I usually do is I have a running variable called offset in my protocol, which I increment every time I have taken care of a field, which makes it very easy to keep track where in the protocol packet array I am, and to ensure that I'm at the right point and doing the right stuff at a certain point. So you see here, I only have the offset and the number of packets I want, and then I add another stuff to it. So I use now this read 16-bit ASCII. And if you go here, read 16-bit ASCII is actually read 8-bit ASCII, shift in 8 bits, doing another read at 8-bit ASCII, and offset +1. And this read 8-bit ASCII actually does all the magic. It calls this function tvb, get GUINT8 on this message tvb, which is actually our packet buffer. So those are where all the packets are at. With the given offset. And then this is a very crude translation from the ASCII code to actually integer code and returning the integer value. So this is 0, this is 9 in ASCII. Now those TVB functions are actually the functions that manipulate or read stuff from the message buffer. And you can look them up in the tvb.h file. Actually, I would recommend doing that. There is a README dissection documentation in Wireshark as well. But I would actually recommend you to look at the actual header files, because you learn a lot of stuff from it, and you might see some stuff that's easier to do, or that allows you to do different stuff than you would expect. For instance, we have a lot of different variants of get those GUINT values. So you can, for instance, read 56-bit if you want to. So I have this version now, which reads me this 8-byte, and I can run it. And again, I will fire up my dissector and hit here example. And when I now do it, I see, oh, now I have it correct. So I have 3 and I have 49. Where I have still a little bit of issue here, but it's pretty much, yeah, it should be 31, 33 together is 49 in hex. It should work out, which is actually a correct length, so I'm not really worrying about that. Or should I? Well, so this code works. Now let's add other stuff to it. Whoa, now I've added quite a few things. So I added my uint stuff again for the remote length, but now I also added stuff to read the remote name and display it. I do that by using another TVB function, get string encoded. So this is a function that retrieves a certain amount of bytes from the packet and then returns my value to correctly encode it. I encode with Big Indian using the message buffer, starting at a certain offset and using the length I've read before. The one thing to consider here is we are in C code, and to use a string in C code, you have to gather memory to store this code in C code. Now you could use all your malloc and free stuff and so on, but you will mix it up and Wireshark use it in a certain way. But we do have our own memory management. And in this case, this is called by setting a certain scope for the packet. Now we have different scopes. We have a packet scope, we have a file scope, we have an EPEN scope, and they're all meant to live at a certain amount of time and for a certain amount of time. Now, the packet scope lives just for the amount of time the Wireshark dissection engine needs to dissect the packet. And as soon as the packet is no longer needed in memory, memory freed or requested using the packet scope is freed. So it's a very memory efficient way. And we only need it here, so we don't need to have this memory living on. So what I'm telling Wireshark is, please give me this many bytes from that offset starting and put it in a memory variable that lives in the packet scope. And I can run it. And it will work. Oh, won't it? Well, still, everything looks clean. So I have a message, my remote interface here, and it's actually written remote interface EF1, and I have a message length underneath. Now you see that the message length now is written a little bit different, 0031. And the reason for that is that I changed the registration for this field to say, oh, you're 16-pin, but you're base hex DEC field. So you're going to be displayed as a hexadecimal with the decimal in brackets. I could do it the other way around as well. So there's no thing, I could do it like that, for instance. And this allows you to write code which is very useful to the end user because it will let him correlate the actual decimal data he's seeing with the hexadecimals that he's seeing in the byte field. Now this remote is working. Let's go to the message itself, right? We want to have a full dissection of this whole stuff. So in the dissection stuff, we do a little bit thing differently. And for a second here, I'm commenting this stuff out here. And just run it. The RAM length, yeah, that's always tripping me up. I have to. I could just comment that out, but I'm more used to if0 so that I don't produce any code. Now I added the message to it, and suddenly I have this thing here. It still looks the same, but the message I added already. So if you see here, I have this message data field, which I added. And the reason why this is happening now is, and it's actually written quite nicely, he says there is a problem and it's malformed. Now, malformed can be a lot of things, but usually what it means is that you try to read information, in this case, bytes, beyond the end of the data he has available. So instead of crashing, he tells you, you did something bad here and please take a look at it. You also get this nice malform packet here. Well, the reason why that happened is that, and this is what I commented out here, is that actually this 49 value, and I will let it keep it in, is the wrong value for the length. It's actually 13. some stuff is going on up there, it's not working. But you can easily fix it by doing something like this. You not only can get information from this message TVB about the actual data, you can get also information, meta information about the capture. In this case, I said, please give me the captured length of this message TVB remaining from this offset, which means it's not actually it might not be the length you're expecting, it might be a shorter length. It's just that many bytes he has left in this message buffer, and it's the captured length. There are different values here. You have different possibilities. So there's a TVB just length, which usually takes the length field from the Ethernet header and stuff like that. So they differ all. But this one gives you just the remaining length he has captured. And then you can do an expectation scan. So you say, okay, this is the length I'm reading, this is the remaining length, blah, blah, blah. And then I'm saying, okay, just give me the messages I want. And I can put it in there. And at the end of the file, I also added now this example verify. So if I run this code now, I see again a wonderful trace. And I have now my message data. And I have this verification here. Wow, cool, I'm done, right? No, because this is still an issue. So I'm reading, I'm not gonna fix it. I'm letting it in there for, letting it be in there for teaching purposes. So somehow I wrote code that's corrected it, but a user who's looking at that and see it. So if you have people with less experience in that protocol version, they won't be able to, there's something going on, there's something fishy going on. And for that part, we actually come to the last stuff we're gonna do in there. Okay, before I do the last stuff, I just want to say how I wrote this verified, not verified stuff. So Wireshark has something, and this just goes to the length of really stuff with thinking that went into this whole dissection engine. So for instance, you can create something that's called true-false string. So it says, okay, this is just a 2-byte value where it say, okay, when it's true, it has to say verified. If it's false, it's not verified. And all we do in the registration of the field is saying, I'm having this field, and it's a true-false string, and it's a Boolean. And I'm just saying, okay, add this field, and he's taking a look at the byte and saying, oh, you're true, then I'm going to put verified in it, and you're not true, then I'm going to be not to be verified in it. So I have this problem again with the length. And what I'm doing now is I'm adding an expert info. Now, the expert infos you have to register. So I actually registered this at EI protocol warning down below. We saw that before. And the expert info now is, in this case, an information from you to the user of the protocol that's telling you, hey, something went wrong, something went not the way it was expected, or you have a value that's on the fringe of what those values should be, or this doesn't look right to me, the sequence numbers are not ordered correctly, something like that. And now the end user, who has lower level of knowledge of the protocol than you have, is able to see this error and is able to work with that error and figure out what's going on. So in this case, we just have the same consideration than before. And again, we have our example. Now we don't have a red one, we have a yellow one because it's a warning. There are certain levels to this expert info, and for that information, I would forward you to actually Richard Sharp did a talk at the SharkFest Europe in 2019, where he made a huge presentation about expert information. But in this case, I have the message data now highlighted yellow, and it tells me warning protocol.
5 minutes to go, Roland. 5 minutes.
Thank you. And it tells me there's a calculation for the payload length, which is 19, and you yielded a longer result than the remaining length, 18, which actually are not the right values. It's just I put in the wrong, but it's easily corrected afterwards. So now the end user who takes a look at the protocol, he can say, okay, wait a minute, I see all the values, but the protocol dissector did something different here, and this is how he had to fix it. Okay. So I hope this was informative. I hope you all could take away something from it. So I just want to leave you with two things. First of all, think before you code. Should be self-explanatory. And the second thing is think ahead. So really take into consideration is who, how, and what trifecta of people who will be using your dissector. It's not always going to be you. And even if it's going to be you, I wrote dissectors about 2,000 lines of code, 3,000 lines of code. I have no clue what to do in every detail of that dissection engine. So even you might benefit if you take a little bit more time to think about certain field names, certain considerations in dissection. And with that, I would say I'm done, and it's time for some Q&A.
I did answer a couple online while you were going there, Roland. There's a few more left there. TVB.
I have no clue. Graham, do you?
Yes, it's testable virtual buffer. And the idea is because we want to avoid buffer overflows in the engine, that you never know exactly how long the packet will be. Like the packet header may say it's 48 bytes, but you only get 24 bytes or something like that. So it allows the proto-tree functions to access that buffer without running off the end dangerously. It's a safe buffer for accessing.
Okay. The second question, where's the main function for the section written, and also how does Wireshark know it has to use a particular registered dissector? Well, actually, the main function for the section is Wireshark just creates the initial TVB buffer and then calls the packet frame. This is what happens. And in some variations, he calls something else, but in the most cases, he calls packet frame. And with that, he just kicks off the dissection, and it goes from there. So the Ethernet dissector is on top of packet frame. It has connected to that. The IP dissector, for instance, is on top of the Ethernet. TCP is on top of that, and so on. And the way this works is every time, just with this dissector, add uint stuff, where, for instance, you can register for an Ethernet type, and you can register that your protocol accesses a certain Ethernet type, or there are dissectors that just take the whole frame buffer. So they have a heuristic dissection on the frame itself, and tell him, do that. And what happens is that there is always a list of dissectors available for each version. So there might be more than one dissector registering for this AP Proto 254. And what is expected by the dissector is it takes the data it gets and then takes a look at it. If it's really is his own data, and if it doesn't, we can actually hand it back to the Wireshark system. So I always return true here, but I could at the same time consider if this is actually my stuff. And if I figure out that no, this is not data intended for my dissector, I can return false. One way to do that, for instance, is by using heuristic dissection. And in my own dissector I wrote quite a few years ago, there is actually one function in there which is called find safety frame, which does nothing else than figuring out, this is a heuristic dissection, figuring out if this stuff is actually meant for itself or not. And as you can see, I wrote that and I have no clue what it does. So I wrote extensive documentation in it to be able to go back and figure out why I made those decisions and do it. I think this is the only documentation you're going to find in the whole file. Yeah, so that's pretty much the question from Amaya, where the main function is, and also how does Wireshark know that it has to use a particular registered dissector. It actually doesn't. The dissector has to know. And if the dissector decides it won't take it, then it can give it back to Wireshark. In the end, the last dissector, if no other dissector takes it up, the last dissector that's being called is called data, which just displays the dump file. It just displays the bytes. Stefan Böck asks, I'm writing the sectors that are intended to be used by both Wireshark and T-Shark. Are there things to consider when caring about performance, e.g. I am appending information to certain fields for use with Wireshark. Is this impacting the performance when being used with T-Shark? If so, is there a way to get around that? Well, the thing is that the dissection engine really doesn't know if you're calling it from T-Shark or Wireshark. But what I would do is you have to consider how much time you spend in those dissection functions. So the longer you need there, if you're calculating stuff, try to avoid loops, try to avoid really big calculations like CRCs and stuff like that. We have code for that, which is a little bit optimized. The longer you take in there, the longer it takes for the dissection engine to run through. And you can actually measure that. So every line you put in a dissection engine has an impact. But besides that, I would just not so much consider it on timing, because this is more a question of your network equipment and stuff like that, how fast you can get the packets in. But I would consider it more a question on naming, because the better you name stuff, and for instance, what I did, I had one issue here, which I normally won't do, is I called this expert info example warning protocol. You should avoid naming reusing fields. You should avoid reusing names, so that you have only a single name for stuff, which makes it easier to put it in certain stuff like JSON and parse it correctly, because you have a single entity to look for, and that this entity cannot reflect 10 different ones. So yeah, that's what I would consider. But you can always stick around later in the development tent and ask the question again. For instance, Jaap is online and he knows way more about this stuff than I do, and he can give you more details on that if you like. Any further questions?
Can you show the final slide again? There we go. For surveys, please fill out your surveys. It helps us to make sure the content is applicable for you guys attending SharkFest, and gives us feedback on where we can improve if at all possible.
Okay. If there are no more questions, then thank you all for your participation.